Hello again and welcome back. I'm Mark with Design Optics Fast. Today we're going to start optimizing the basic shapes of optical systems with Optics Studio, and we're going to start with the simplest imaging lens there is, the landscape lens. Now don't confuse this with just any camera lens used to take pictures of a landscape. We mean a landscape lens in its optical design sense. A lens and a stop that forms an image of an object which is a long way away from the lens. If you haven't watched my Where Do You Start with Imaging System Design video, I recommend you watch that first. We're going to use a straightforward specification for the lenses in the Basic Shape series. The lens should work across the visible range. And in this case, I'll take that to mean using the F, D and C spectroscopic lines, which are often used as a placeholder for visible in lens design. And that will give us 0.486, 0.588 and 0.565 microns wavelengths. The D line will be the primary wavelength. The lens will be f5 and have a focal length of 50 millimeters. The field of view will be plus or minus 10 degrees, and the object will be at infinity. This is a core specification for the landscape lens, as it assumes the thing being imaged is a long way away. That makes it different to a portrait lens where the thing being imaged is close to the lens, or a microscope lens where the object is extremely close to the lens. Generally, a distance greater than 20 effective focal lengths is considered at infinity and therefore a landscape lens. Our target is to get the best possible RMS spot size averaged across fields and wavelengths, and we'll go through all the basic shapes until we get a design that has an RMS spot size comparable to the Airy disk. Once we achieve that specification, we'll increase the field of view and or make the F number faster to make a more demanding system. We'll investigate all the basic shapes of imaging systems this way. This video will cover the optimization of the landscape basic shape. So let's go. Okay, so let's get started. Start up Optics Studio and hit File New. I've set up my user interface in the way I described in my UI tweaks video. Now, since the stop is going to be the first optical surface in the system, I'm going to use float by stop as my aperture definition. So in the Aperture tab, Aperture Type, float by stop size. With an f5 lens and an effective focal length of 50 millimeters, the entrance pupil diameter is 10 millimeters. So set the semi-diameter of the stop surface to 5 millimeters to give us the correct entrance pupil diameter. Now, of course, you could just enter entrance pupil diameter directly, but I prefer to use mechanical definitions rather than optical definitions. Next, we want to open up the field data editor. And we're going to use the Fields Wizard, and I will choose equal area Y fields. I want 3 fields with a maximum field of 10 degrees. I just click on OK. And I want to order the fields by Y angle. Because the system is rotationally symmetric, you don't need to specify fields in -y or in plus and minus x. Then open up the wavelength dialog box by double clicking on wavelengths, and here in this data choose the presets F, D and C, select the presets, and that fills in the wavelengths that you want to use and sets the primary wavelength accordingly. What we're going to do now is click on the image surface and press Insert twice. Set the stop surface thickness to 5 millimeters. Set the lens thickness to 5 millimeters and make the material NBK7 and set the back focal distance to 50 millimeters. And if we now just look at the two-dimensional cross section, you can see I've just got a flat piece of glass in the layout drawing. Now on the second radius of curvature, I'm going to click this little box next to the radius of curvature, and I'm going to choose F number, and I'm going to tell Optics Studio I want this to be an f5 lens. And you'll see here that we automatically calculate the radius of curvature needed to give us an f5 system. And what's more, if I change the previous surface radius, you'll see that that automatically updates to maintain the condition that I have entered, no matter what value I put in there. I'll just leave that at infinity. I want to make a few small changes here before we go any further. You'll see that Optics Studio has made the lens just big enough to capture all the light. And I actually want it to be a little bit bigger than that so that I've got some margin for error. So here where it says clear semi-diameter margin in millimeters, I am going to enter a 1 millimeter semi-diameter margin, and you'll see now that the lens is made larger than it has to be in order to let the light through, and so we now have some space here for mounting of the lens. And we'll go on to mounting later, but it's important that the optical part of the lens be slightly larger than it needs to be. I'm also just going to add a surface prior to the stop and make its thickness 5 millimeters also, and I'll just set the lens layout drawing to go from the new surface one so that you can see that. I'll set its clear semi-diameter to 0, which means that it won't draw. The last thing I'm going to do is go to the optimization tab, and on the quick focus I'll set spot size radial, use centroid, OK, and that just adjusts this thickness to get me into best focus for best RMS spot size. The last thing I'm going to do is go to Analyze, Rays and Spots, Standard Spot Diagram, and hit Show Airy Disk. And you can see that this design is nowhere near our image standards yet. The airy disk radius is about 3.5 microns. The RMS radius is 54, 90, 127 microns. So I'm nowhere near a specification yet. But I'm going to save the lens at this point. And I'm going to save it as landscape template. I already have one, but that's all right. And what I've got here now is a template of an f5 landscape lens. Note how we set the lens up, so all the first order properties of the lens are cooked in via the aperture, field and wavelength tabs of the System Explorer, the f number solved in the lens data editor, and the semi-diameter of the stop surface. You can modify these for any specification that you have. This is a very, very general way of setting up a lens. Now let's move on to optimizing this lens. So we'll go back to the Optimize tab and we're going to open the function called Optimization Wizard. Now in the Optimization Wizard, under Image Quality, for the optimization function, Image Quality, choose Spot, and you can see that you can specify X and Y weights for the spot. We'll leave them both at 1 because this design is rotationally symmetric. We'll leave distortion unset for now. Remember that distortion is separate to image quality as it affects the location of the spot, not its size. Under pupil integration, we're going to choose Gaussian quadrature and set the number of rings equal to 5. We'll cover Gaussian quadrature in a separate video. But for now, just know that this gives us exact control of all aberrations up to the order of r to the power of 2 times number of rings minus 1. So with 5 rings, we have exact control of all aberrations up to r to the power 9, and that's certainly good enough for a singlet. Then under boundary values, we're going to select the boundary values of the glass such that we have to require a minimum center thickness of 2 millimeters, a minimum edge thickness of 2 millimeters, and a maximum center thickness of 15 millimeters. So by changing the radii and thickness of the lens, we're also going to require that the center and edge thicknesses remain within what we consider to be physically realizable. For air gaps, I'm going to specify a minimum air gap of 1 millimeter at the center, 1 millimeter at the edge, and leave the maximum at 1,000. We don't really care how big air gaps get, we just want to prevent components from physically touching. We're going to leave everything else alone for now. We'll discuss improving manufacturing yield in a later video, but for now we're just going to go for best nominal performance, press OK, and that will build the merit function for this design. And again, we'll discuss exactly what the merit function is in a separate video, but for now just think of it as measuring the RMS spot radius of the lens averaged over the defined field points and wavelengths, and the optimizer's goal is to minimize this whilst not breaking the mechanical constraints we've set. So let's now set the variables for this design, and we can do that in two ways. One is on the thickness solve function, we can choose a variable. In this case, we're making the distance of the stop surface to the lens a variable, or we can just use the keyboard shortcut Control-Z, and I've made the thickness of the lens a variable with Control-Z, and I'm going to make the back focal distance a variable, and I'm going to make the radius of the first surface a variable. This F-number solve will automatically update to maintain this lens as an F5 lens throughout optimizing. And now let's just hit optimize. You can see the initial value of the merit function is 0.02. Think of that as being very related to the RMS spot size. And if we hit the start button, very quickly, 0.3 of a second, the merit function is dropped by about half. And if we have a look at what we've got, you'll see that we now have a lens where the spot has improved significantly. The spot is now 40 microns, 38 microns, 56 microns, much better than it was, but still a long way away from our target area radius of 3.5 microns. You can see that the center thickness has moved to being exactly 15 millimeters. And thickness is a weak variable. We'll usually go to the maximum allowed value. Designers often simply set the thickness of a lens to its maximum allowed value and don't optimize it. Note also in the 2D layout the slightly odd drawing of this first surface where it appears curved and then becomes flat. The rear surface, on the other hand, is curved all the way to its edge. Now, don't worry about this for now. This is all to do with the details of designing edges for lenses, and we will cover this kind of thing. For now, just recognize it's outside of the optically important part of the lens, and we'll come back and look at edges as the design matures. Now, from the point of view of the optimizer, we have 4 variables, but they're not all equal. There's only the front surface of the lens which can control radial or pupil aberrations, and the distance from the stop to the lens which controls the field aberrations. The thickness of the lens itself just moves to the maximum that we allow it, and if we allowed it to go to 30, it would go to 30. And then the back focal distance simply keeps us at best focus. We just don't have enough degrees of freedom in this design to get close to the diffraction limits that our specification requires. Also, this lens is so simple that it will not benefit much from using the global optimizers. The hammer optimizer is used to extensively improve a design. You'll see if we let it run, it makes a very tiny change right down here in the noise of the merit function, but it will make no significant change to this lens because the design is just too basic. There's just not enough degrees of freedom for us to find any further gains. But even with that really small change that we saw, it came by making this surface slightly more powerful. And this is going to be discussed a lot more when we get on to discussing manufacturing yield. I'm also not going to try to optimize the glass at this point. There's only one glass, and Optics Studio will choose the highest index glass it can find. NBK7 is a fine optical workhorse glass, and we won't make any significant improvements until we move to the color-corrected landscape lens. This shows us that a singlet lens in the landscape configuration can't give us the imaging quality we need. The lens aberrations are dominated by focus and spherical, which you can see on the Analysis tab, the aberrations, ray aberrations. You can see focus, spherical and chromatic versions of both of those. If you're not familiar with array fan plots, don't worry, because we'll be covering them in a subsequent video. And if we look at the tidal diagram, you can see that surface 4 is adding a large amount of spherical that just can't be corrected. And so the design is just dominated by spherical. The RMS spot size is in the 40 to 55 micron range and nowhere close to the 3.5 micron diffraction limits. But I want to teach the basic shapes of imaging systems, and I don't want you to get the message that singlets aren't useful. In fact, many optical systems in production are singlets. This lens has an effective focal length of 50 millimeters. What would happen if we scaled the lens to, say, a 10 millimeter focal length? Well, in the Lens Data Editor toolbar, there is a Make Focal tool which scales the lens to the desired focal length. And using it, if I just tell it to use a 10 millimeter focal length, the whole lens is scaled down, still f5, but it's now giving me a 10 millimeter effective focal length, and I've got a spot with an RMS radius in the 8 to 12 microns region, much closer to the 3.5 micron diffraction limit. Let's scale it again down to 5 millimeters. And you can see that I've got something that is getting close to the Airy radius, 4 to 6 microns, getting close enough maybe to have an argument. And take it down to 2.5. And we've got RMS radii less than the Airy radius. So as we've scaled the lens, the f number has remained fixed at f5 and the aperture of the lens has reduced along with the focal length. So we have a much smaller lens than the one we set out to design. My point here is about the basic shape of the landscape lens. This basic shape can give us good imaging at small apertures, as when the lens gets smaller, we naturally get closer to the paraxial properties of the lens. If you think of all the small lenses we use these days, from mobile phones, car backup lenses, drone lenses and such like, they give sharp imaging, at least in part, because they are so small. The downside here is light grasp. A smaller lens will emit less light than a large one by the ratios of their diameters squared. Additionally, the image size scales and becomes proportionally smaller, but this plays into our hands somewhat. Modern silicon detectors are small in any case. One of the big changes in optical design in the latter part of the 20th century was the replacement of photographic film with CCD detectors, which are more sensitive and which allow for post-processing of the image to combat noise. So the 50mm focal length landscape lens is not much use at f5, but the 2.5mm focal length landscape can be very useful. So let's summarize what we've covered. Start with a specification and set up a base system that encodes the first order and constructional data for the system. We set up the lens so that all the first order properties of the lens were set up in the System Aperture, Field of View and Wavelength tabs of the System Explorer, and in the Lens Data Editor by setting the size of the aperture stop and the f number of the lens directly. This gives us an easily scalable template for any design involving a landscape lens. We optimized it for RMS spot size averaged over the specified fields and wavelengths. Using a Gaussian quadrature method that is exact to r to the 9th in wavefront aberration, given the setup that we did in the optimization wizard. The lens produced was far from diffraction limited, but could be easily scaled to scope out the regions over which it was capable of diffraction limited performance. Think about what each variable in the system is doing. We need to scale by a factor of 10, which is a good indication that this basic shape is not adequate for our specification. So 1. Set up a base system that encodes your specification in the System Explorer and Lens Data Editor. 2. Build a merit function that optimizes the desired image quality as well as providing boundary and other constraints that the design must work within. 3. Hit the big green Optimize button. 4. Analyze the results you get. Think about what each variable in the system is doing. Use the Make Focal tool to see how far from specification you are. Thanks for watching.